Good day. Today we are presenting our work regarding efficient feature selection for electroencephalogram-based authentication. The work was conducted in Università Politecnica delle Marche in collaboration with Prof. Marco Baldi and Prof. Lorenzo Scalise. We will talk today about several topics. We will start by introducing what is EEG-based authentication. Moving on to discuss feature extraction and selection process of the EEG-based authentication. Moving on to discussing the classification algorithm that is used to classify and build the EEG-based authentication system. Next, we will discuss the results that was obtained from the previous pipeline. Finally, we will conclude with some messages. Of EEG biometric, we need to introduce three questions. First of all, what is a biometric? A biometric is physiological feature shared by all humankind. For example, fingerprint or iris print or face print. In this research, we are introducing the EEG print, which is a biometric based on the brain waves. Another question is, what is the advantages of EEG biometric among all other biometrics? In fact, it is more resistible for spoofing, and it needs a liveness test. For example, other biometric could be mimics or taken from a dead body, but for EEG biometric, it's more strong and more reliable. The third question to be answered is why we are exploring the EEG-based authentication. To answer this question, we are introducing the following graph. This graph represents the EEG-based authentication in the literature. It shows the number of publications on PubMed database using the query EEG and authentication or biometrics. It shows that there is an increasing trend starting from the year 2000, and it starts to increase until now. So it's a topic that needs to be explored. We have found that there are a lot of gaps and challenges need to be addressed in order to have a stable and in real life EEG-based authentication system. Those challenges include the universality of the biometric, the permanence, and the uniqueness. Also, the collectibility, the protocol of recording the EEG data, and also it should respect the user privacy. Additionally, the security of the system must be also considered, the stability, and also it should be a user-friendly. Under each category of those 9 categories, there are a lot of questions and a lot of gaps that need to be explored and need to be addressed. Our aim in this work is to find efficient criteria for selection of features bearing most of the identity information by firstly excluding the misleading features, and secondly by determining correlated features that cause redundancy. This will lead to dimensionality reduction, which in turn decrease computational efforts and improve performance of EEG biometric system. By taking the general pipeline of EEG biometric system, we start by understanding what is the problem in hand and what we are trying to find. After that, we have to choose the trait of the biometric, which is in our case the EEG signals. We need to extract features that represent the personality of the subject and the personality of each individual that able to distinguish it from other. Finally, we need a matching algorithm or a classification system that can tell those features are belongs to which subject or to which person. We need to also to evaluate the performance of this matching algorithm. We need to have a feedback to modify any point of the previous points in order to have a stable and reliable system, in order to implement and design the system that could be used in real-life applications. To conduct our research, we used two datasets. The first dataset is simultaneous task EEG workload dataset, or known as STU dataset, which include two sub-datasets, resting state and mental workload. It includes 48 subjects and, and data taken from 14 channels and 2.5 minutes of recording. The second dataset is EEG alpha wave dataset, which has 20 subjects, 16 channels of EEG data taken for 2 minutes of recording. Some pre-processing to the signal to ensure that it's clean from any artifacts. To do so, for the two dataset, we segmented the data into 60 segments. The segments are 80% overlap with a length of 5 seconds. This will be the core segments that will be entered to the system. We used after that a Butterworth filter from 3 to 40 Hz bandpass filter with first order. Next, we removed the spikes by replacing the values above 97% quantile and below 5% quantile by the mean value of the signal. The preprocessing applied to the EEG alpha wave dataset is almost the same. We applied the same segmentation and the same filtering, but we obtained a less number of segments because the recording is shorter. Extract the features that represent the EEG signals. We extracted features from 5 classes, starting from statistical features, moving on to extract features related to the power spectral density. The next class is features related to entropy, like permutation entropy, spectral entropy, the singular value decomposition entropy, approximate entropy, and sample entropy. The following class is related to fractional dimension, which was extracted using 3 different theorems. The final class is the trended fluctuation analysis. The DFA has a major advantage of its suitability for non-stationary signals. Overall, we have 17 features in full feature set. Now, we need to reduce those 17 features into a smaller subset of features that have the same performance but less computational efforts. In order to select features, 4 different methods were considered. Firstly, the cluster map, which analyzes the correlation between the features. Here we can see in the plot that we have 4 clusters of the features. Each cluster contains features that are correlated to each other. This method gives us 4 different features. The next method is the ANOVA F-score, which gives a weight for each feature. We have found that 5 features are more contributing in the analysis. The next method is the logistic regression weight, which gave us only 3 features. The final method is the fused feature set, which have a union of the previous 3 feature set. This union gives us a list of 9 features that are the most suitable for the work. This data was analyzed using 3 different classification methods. Using the artificial neural networks, for each dataset, a different architecture were used based on trial and error. Next, we use the k nearest neighbors classification method. And experimentally, we have found that k equals to 1 give us the best values. The last classifier is the extreme gradient boosting, which is a very new and very promising classifier. Now, it's time to show the results of the previous analysis. We divided the analysis into 2 parts, an internal comparison and an external comparison. By starting with the internal comparison, the results are demonstrated in the following figure. We can see that this figure is divided into 3 groups. The first group contains the information regarding these 2 datasets in resting state, while the second block contains information of 2 datasets with mental workload case, and the final block contains information about EEG alpha dataset. In each block, we can see we have 5 stacks. Each stack represents a feature set, starting with the full feature set, the fused feature set, next the cluster map, and the ANOVA F-test, and finally the logistic regression weights feature set. We can see that the XGBoost outperforms other classification algorithms in all cases. Also, it's noticeable that the fused dataset performed similarly to the full feature set, knowing that the fused feature set contains only 9 features, while the full dataset contains 17 features. This means that the fused dataset can have a performance similar to the full dataset with lower computational efforts and with lower complexity. The fused dataset is 4 times faster to be extracted from EEG signals in comparison with the full feature set. Moving on to the external comparison, our results shows more or less similar performance than the ones found in literature. However, we have achieved significant saving in time and complexity of the system by using the feature selection methods. However, more objective comparative regarding the efficiency of the proposed approach is, is to be conducted in the future work and in the follow-up work. As a final conclusion of this work, we can see that feature selection criteria for the application of EEG-based authentication have not been studied in previous literature. So our work contributing by bridging a gap in the open challenges found in the literature. In our work, we used 4 reduced feature sets and tested on 3 different EEG datasets. The results of this work shows a significant reduction in computational time between the full feature set and the reduced feature set, while the performance was almost the same. As a final saying, we have found that EEG-based authentication is a promising biometric to be implemented in real life. In our work, we have achieved a step forward towards real-life implementation. However, there are still big gaps to be bridged and more challenges to be addressed. Now we have reached the end of this presentation. I would like to thank you very much for being here and for attending this presentation.